Hello everyone, I hope you're all doing great. My name is Ali Muhammad and I'm here presenting implementation of Arabic Syrian dialect TTS service. First, let me begin by expressing my gratitude to be participant of this conference and my apologies for not being here live with you due to circumstances beyond my control. Our paper entitled Arabic Syrian dialect text-to-speech service implementation authored by Professor Hadi Saleh and me, Ali Muhammad, in HSE University in Moscow, Russia. And many thanks to our both academic and technical colleagues, Munaf, Kamil, Bashar, and Samer. And this is are the contents of our presentation that summarize our journey to implement this service. Let me start my presentation by saying that natural language is any communication system that happens without any intentional human design or planning. This system could be written, spoken, or even signed. And NLP is the idea of integrating natural language into technical applications, such as extracting text from images or transferring text into audio and vice versa. Even that natural language is a common worldwide concept, but not all languages get the same interest from NLP. And Arabic language is one of these languages, unfortunately. Arabic language is a spoken language around the Arab nations and around the world by Muslims. And it has a standard version and five derived dialects from it. And the Syrian dialect considered the nearest one to the standard Arabic. And it was the main reason why it was adopted by companies like Netflix to translate their own movies and series. And thanks to the research in the Arabic countries such as Qatar, UAE, and Saudi Arabia, the interest of Arabic NLP increased during the past years. Text to speech service is the task of NLP that concern about synthesized speech from input text. And it was improved over the years, not just to make the text spoken. It also urged the needs to make it more human-like, with like natural and comprehensible. Our journey to implement an Arabic TTS service started by searching the market for available solutions. But unfortunately, these solutions provided by big companies such as Amazon or Google, they were had two main issues. The first one, it was on-cloud solutions. We needed on-premise solutions because to preserve our users' privacy. And the second one, even with some of their models, they had some challenging issues dealing with Arabic language for pronunciation and mostly for characterization. So the result for this, we proposed to create our own TTS model based on machine learnings and to make it synthesized a speech using the Syrian dialect for the common language, for the common sentence in case it happened. And to integrate this service to as a web service using API to be deployed and used as a standalone service by any external services. So after deciding to develop and implement our own customized TTS service, we started doing a literature review about the history of TTS in general and Arabic TTS specific. So we found out that it used multiple approaches such as statistical approach using hidden Markov models and improving the results by implementing neural networks and machine learning techniques. And the same approach were applied for Arabic TTS. And one of the main interesting studies about Arabic TTS was the one done by Fahmi Yal that proposed a speech synthesizer for Arabic language using Tacotron, an RNN architecture followed by WaveGlowNet to produce the synthesized audio. Before comparing and providing some information about the architecture that we decide, we need to define some terms such as mean opinion score, which is the accuracy score that we're using to define how good our service is, and it's actually based on human interaction with our services in regarding of multiple points such as analness and is the audio speech is understandable or not. Phonemes are a sequence of characters that represent how the sentence is pronounced. So basically, it's a unified language to be used, and which is found better to be used as an input to the TTS service instead of different characters such as Arabic, English, or Slavic characters. And male spectrogram are a subset of frequencies that represent the pronunciation, the sound of each phoneme. During our research for suitable architecture to build our TTS service, we faced two, and transformers. Toctron 2 was implemented by Famiel and transformers with his proven efficiency in different NLP tasks. Tactron 2 is basically has two networks. The first one uses RNN to extract the features from the text sequence, and the second one is the wavenet that generate the male spectrogram corresponding to this sequence of phonemes. While transformers, on the other hand, depends on the attention mechanism between its encoder and decoder, which has not reduce, eliminate the recurrent networks connections between the layers to faster the training and to extract the features much faster. Implementing a transformer instead of tachytron will allow us to parallel training and improved in training procedure and the accuracy. And based on the provided table, we show that it provide more MOS score and more real-time factor on both CPU and GPU. Some research shows that using transformers by itself doesn't provide the wanted accuracy or naturalness of the output. So they developed a fast speech uh, architecture for English language that implements transformers with an additional features to help get more real, natural synthesized. And this fast speech has three main components: feed-forward transformers, which has multiple layers of encoders and decoders based on transformers attentions, and include in the middle a length regulator that would generate double the phonemes based on their pronunciation, depending on a duration predictor that is trained simultaneously with the code with the fast speech itself in order to predict the length of the phonemes in order to match the phoneme length with the number of mil spectrograms corresponding to the pronunciation of each phoneme. As we mentioned earlier, we're planning to deploy a standalone service which has the following architecture: a user interface, just a sample to test the service itself, an API server that is responsible for requests from user interfaces, and to store the data and handle speech synthesized models. Database to save request and users informations, recording properties in order to help the users shows the rate of their recordings, and TTS module that implements our machine learning model to transfer the text into spoken audio. To implement our TTS model, we need to train it, and according to the following workflow that start with collecting text dataset, review it, clean it, fix any misspelling in it, then record this uh, native Arabic speakers with Syrian dialect, and high pronunciation quality in order to make sure that the dataset is clear, clean, and following some of the conditions to produce high quality audios. These audios and dataset are reviewed by an Arabic specialist and always feedback to the recorder to improve his recording and to clean the dataset. After make sure that these records are valid and this dataset text are valid, we combine them to generate metadata, which has multiple records. Each record is a pair of text and name of the audio file, corresponding audio file. Then we send it into the trainer to the aligner model in order to align this text, which is are converted into phonemes, into with the corresponding male spectrogram that are generated from the recorded WAV audio. After training the model and generating the pitch and the duration data, we send it to start training the TTS model that depends on the fast forwarding transformers. And we save the result as the final TTS model. The service API for this has the following workflow where there is an Arabic text that should be inputted. Then we transfer it into a phonemes based on the standard transformation function. And we predict the male spectrogram using our TTS model that should be then used to generate the WAV audio and convert it into an audio file or base64 to be used by the user or any other application. We conducted an evaluation for our TTS model using a form that was sent to 20 people from Syria, from different cities in Syria. Uh, each one has to evaluate 10 sentence based on the following criterias, and eventually we got the following MOS score by 4.42, which indicates that our solutions is natural in speaking, understandable, and most of them, 80%, they accepted to be used as to be used in other applications. To come to a conclusion to this presentation, we proposed an implementation of a TTS service based on machine learning techniques that produce a speech in Arabic language using Syrian dialects for the common sentences. We did this by reviewing available solutions, especially Tactro and transformers, investigated how the fast speech architecture that is based on transformers, how does it work, and how to train it. We created and built our own data set, trained the models, and integrated into a web service that got evaluated by users and showed us a high accuracy corresponding to the response of the users. For future prospect, we're trying to improve the recording admin panel in order to help the users to understand more about their WAVs quality and to enable reviewing and the checking through this admin panel, and eventually implement auto directorizer and add more feature to TS to handle the sound, and add more features to our TTS model to handle the speech and the tone and the voice of the speaker of the TTS. These are some of the references used in our research, and thank you very much for listening. I'm glad, really glad to be